Hello, my name is Trevor Heridono, and today we'll be discussing Lab 4 Physics 2212 Circuits and Capacitors. In this lab, we will predict the behavior of circuits containing resistors in series and in parallel, using multimeters to measure the actual values in conventional current and potential differences in the circuits and examine the behavior of ohmic resistors and capacitors. Fundamental concepts covered include the loop rule and the node rule. The node rule states that current that comes in equals current that comes out. Additionally, if at some point that current gets split, when you add all the currents back together, it will equal the current when they reconvene. The loop rule, a principle of energy conservation, says that the potential difference rounded will be equal to 0. We will also use Ohm's law to calculate the resistance. The general form is showed, but we can also use the following equations depending on if our resistors are in series or in parallel, which we will explore later. A brief preview of the results shows that predicted results arrived at by using the rules mentioned before match any experimental data. Greater resistance resulted in longer charge and discharge times, and the final RC that was calculated was 5.9 per second, which we will also see later. We will do 7 experiments using a FATLab's computerized circuit simulator. Our system will be what is measuring our current and potential differences, and our surroundings will be the circuit itself. First, we construct a simple circuit using the following. In order to predict the conventional current, we can use a combination of loop and node rules. By node rule, I1 and I2 are both 1.5 volts and equal. Since the resistors are in series, total resistance is 147 ohms. We can calculate that the current is 0.020, which is the actual current. In reverse, it will be negative 0.020. Next, we take the same circuit but replace the second ammeter with a voltmeter. We predicted that the potential difference is 3 volts and that the current is 0. This is because voltmeters have high internal resistances, so current flow essentially stops, and it is also an open circuit. The actual results match our predicted results. Now we're going to close the same circuit with a wire, and we're going to measure the potential differences between every point on the diagram to the right. I've displayed a table with my results. We can use this to prove the loop rule, which says that the round-trip potential difference must be equal to 0, and an example of this is shown below. Now we're going to redo the circuit with a 100 ohm resistor and ammeter in parallel. We can see that the current increases. This is because by making them in parallel, some of the current runs into resistors and some of them do not. And when they reconvene at the end, the total current goes up. This can be proven with the formula for resistors in parallel, which is shown at the bottom. Next, we want to calculate the resistance for the following values, which can be done using Ohm's law. As you can see, our top 2 values are off slightly, but this is due to the inaccuracy of an ammeter. Here we are asked to construct a resistor capacitor, or RC circuit, with a 200 millifarad capacitor and a 9-volt battery. We will measure the time it takes to charge and discharge the resistor. First, we run the experiment with a 10 ohm resistor, and then we repeat it with a 20 ohm resistor. As you can see, the second trial takes longer because more resistance means it takes longer for charges to move and for the potential difference to change. Now we're going to make an RC circuit with a 30 ohm resistor, our light bulb, and also charge the capacitor. Then we'll remove the battery from the circuit and measure the potential differences as the capacitor discharges. We will do this every second for 20 seconds. My table with experimental values is shown to the left. Our goal is to solve for RC, which is our time constant. We can do this by plotting a linear regression of the natural log of V over V naught, where V is the potential difference at time t and V naught is the initial potential difference. From the following equations, we can see that the slope of this plot is equal to 1 over RC. Therefore, we can solve for RC. My slope was negative 1.1682, therefore RC is 5.94 seconds. There were very few discrepancies in this lab due to the experiment being conducted via a computer simulation. However, I could have made mistakes by not stopping my timer evenly back when I was plotting data every second to find RC. Some questions asked in the lab were, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? Well, real ammeters are not perfect, unlike the ones online, and they would still have a non-zero resistance even though it was very, very small. In turn, this would still affect our current readings. And what if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? In our online experiment, a capacitor charged almost instantaneously. Obviously, in real life, this is not the case. It would probably take longer. Also, unlike in the simulation, real-life wires have very small, non-zero charges, which would also affect our results. Some parting remarks